Thanks for the introduction, Jeffrey. So I'm going to talk about Notebook, which is a plugin that I've worked on for Jupyter. And if you've been in the last couple talks in this session, they set this up pretty well in that we're all kind of thinking about this kind of reproducibility problem that comes from the mutability of state in notebooks. So as Jeffrey mentioned, I'm a data scientist at Stitch Fix. And I spend a lot of my time doing exploratory data analysis in notebooks. And this kind of came out of sort of a what I've thought about if notebooks worked differently from how they did. How could I make the way that notebooks evaluate kind of better match my expectations for exploratory data analysis, while kind of encouraging me to have better habits of keeping things in order. Thanks to Joel and David for the setup. If you were in those talks, they gave a very good introduction to why this is a problem, why you should care about it, and some ways that to think about addressing it. And so I'm going to kind of continue in that vein, and I'm thankful for them for setting that up. I'll spend a little bit less time on the motivation, but kind of recap that a little bit if you weren't in either of those two talks. So I'll talk a little bit about the motivation for this. I'll spend a lot of time kind of going through the features, exactly how it's implemented. And spend some time in a demo and talk a little bit about possible future directions for this. Actually, I'm going to go do this in Notebook. So I've heard on good authority that emoji compute is the future of Jupyter Notebooks. So this is kind of recapping what this issue is in a small form. If I assign some value to a variable, do some computation, and then mutate that variable, and I have some different value here. If I was to go up here and rerun this, then I have something that's inconsistent with like the linear apparent state of the ordering of these cells. And even worse, if like I've run this another couple times, then I'm going to be even sadder. This is just another kind of the same exact thing, but with an array, so it's less fun. Basically, showing the same thing there. So there's I think a reproducibility gap in the notebook model, and I think this is something that like a lot of people are thinking about from a lot of different directions. And this is just like one small piece of this, where I'm particularly thinking about this issue of how every cell modifies the global state and how that leads to kind of dangerous situations in notebooks. So on one hand, we have this ability for every cell to modify the global state, no matter where it exists in the notebook. And this is kind of great for like being able to move around and play around with data, like with a very low barrier to entry for exploring things. But it kind of has this intrinsic inconsistency, which is that the presentation of cells is linearly ordered, but the execution of cells is not necessarily linearly ordered. So you can easily modify the history of your notebook in the sense that you're modifying what looks like is something that happened earlier on the notebook, and then end up in a situation where the execution order and the presentation order don't match. So there's a few possible solutions to this, kind of that are already common practice. One is to have append-only cells. This is how console IPython works. And here you get consistent history for free. I think you sacrifice some flexibility. You can no longer kind of go back and edit history. You also can't kind of inspect history as well. So I think that that's nice for the consistency property, but I do think you lose something by going into the kind of append-only regime. And the other kind of de facto standard approach for notebooks is if you want something that's reproducible, then you just restart the kernel and rerun all the cells. And that works, but that's kind of a painful workflow, right? If you're in the middle of some exploratory analysis, you don't want to take the time to restart the kernel, rerun all of your cells, and you'll often, or at least I'll often end up with a notebook that I'm like, OK, maybe I'll do that later, but I'm not going to do it right now. And then I come back to it a month later, and I have this thing that I have no idea how it got to be in the state that it is in. So another approach is, well, what I'm going to talk about here with Nodebook. So what is Nodebook? Sorry to any Node.js users. Node isn't a graph node. Term's a little bit overloaded. I made a temporary working name for this, and then kind of just left it. So that's how it got its name. It's Python only, so it plugs in fairly deep with Python. There's no reason why you couldn't kind of implement these principles with another language, but that's not what I did here. And the main thing that it is it's an execution framework with a strict point of view on linear cell ordering, so that the execution of cells matches their linear presentation order. And this kind of, and I'll talk in detail about how this is implemented, but first kind of to give an overview of some of the properties that you get out of this is you can get dependency tracking. So in Notebook, each cell tracks its inputs and its outputs. And so you can track the dependencies between cells. It includes immutable execution. So cells are executing in a sandboxed local scope and not modifying the global environment. So that each time you rerun a cell, it's going to be running in the same environment as it was run on a previous execution. You can get cascading invalidation. So this is similar to what was just presented in the Dataflow kernel talk, where if a cell output changes on rerun, then we can track and invalidate cells that depend on that output. And then another thing that you can get is accessible intermediates. So if you add a new cell, the inputs for that cell come from the position in the presentation order. So you can inspect values as they kind of existed in linear history. So with that, I'm going to do a quick demo, which will hopefully work. So this is the same example with emoji compute. And so here, I've done the same thing. I've run all these cells. But now this value of x is the value of x in linear history here. If I go up to this previous cell and rerun that, it's going to depend on what x was set initially. If I run this multiple times, that's not going to affect any of the outputs. So you have consistent history here. And if I was to change something here, let's see, can I do the emoji keyboard? Yeah. So let's change that. It's going to invalidate all of the cells that depend on that. So here, pay attention to these x's that were marked on the input cells here. That's how I'm indicating the invalidation. I think it would be nice to have some additional GUI work on this, but you can see it's tracking the state there. And if I want to rerun something down here, it will get the previous. We'll rerun the previous cells as needed, so it doesn't have to rerun that second cell there because it wasn't modifying anything about the state of x, but it need to rerun that third cell there. And so also if I need to rerun this cell, I can as well, and it will depend on its position there. Same thing with the array example that I showed on the other slide, where I can do something like that and track its position there. I can do more things too if we want to do if we want to do something like add in another dependency. So now we have something where the state of this list depends here this on the previous value of x and y as well. If I change that, then we can see the changes propagate there as well. OK, so that's kind of a toy example. I'll do like a little bit more of a data analysis example later. But at this point, I kind of walk through how all of this is implemented. So I talked about kind of 4 features, and I'm going to walk through where those all come from. So the first thing I mentioned was this dependency tracking property. So each cell is tracking its inputs and its outputs. The way that that happens in Notebook is that I parse the AST to determine what the cell inputs are. So any time that I read from the AST that the cell is loading some value, then I track that as an input. And any object that is modified in the cell, I'm interpreting as an output. So for example, in this array example, the first cell is storing something into x, so I'm tracking that as an output. The second cell loads something from x as an input, and the third cell both loads and modifies x, and the fourth cell loads x as an input. So from that, I can match those dependencies to the cells that they came from. OK, so the second and closely related property here is immutable execution. So I mentioned for this that cells are executing in a sandboxed local environment. And this is kind of like where the meat of Notebook really is that I'm serializing any modified objects. So really, there's serialization is happening at each step in this process, serialization and deserialization between cells. And that's how I'm guaranteing this immutable environment. So when a cell is executed, I know from the dependency graph that what its inputs are, so I can load and deserialize those. And then any things that are modified from their initial value, I can serialize and store as outputs. And then I can have consistent execution regardless of when the cell runs by just being able to match up the inputs to the appropriate outputs. So I'm going to kind of walk through that kind of in more detail because I think it's important. So exactly how that happens for cell 1 here is, OK, first of all, I can tell from the AST that there's no inputs to this cell. It's not loading anything. So I'm going to execute it in an empty environment. Then I can tell that x is modified. So this I'm able to tell because I'm serializing the environment pre and post cell execution. And so I can tell that the value stored in x after execution doesn't match what was in x before execution. In this case, trivially so, because x didn't exist before execution. So I know x is modified. So I'm serializing x. I compute the hash of the serialized value of x. And then I store alongside this cell a map from x to the hash value of the serialized version of x in that cell node 1, so that I know what object to look up if I need to access that input later. And then finally, in the kind of global Notebook data store, I'm going to map that hash to the serialized value. And this can exist either in memory or on disk. There's an option when you initialize the Notebook to have either this be in memory and kind of more ephemeral, or on disk. And there's all the trade-offs you would think of for those. But the key thing is that there's this Notebook data store that now anything that needs to look up this value at a later point can come and can pick that up from. OK, so then for the next cell, this cell has an input of x, and I can so I'm enforcing linear cell execution. So that input of x has to come from the most recent previous cell that had an output of x. In this case, there's only one immediately previous cell, and I can just trivially match that up as the cell that modified x and that we will use as the input for this cell. So I look up the hash of that value for x from the cell node 1 map, and then deserialize x from the notebook data store. And now I can execute the cell in this environment with the appropriate value of x. And in this case, from my pre and post execution serialization, I know that x is not modified, so this cell doesn't have any outputs. OK, and then moving on to the third cell here, now we have one that's both taking an input and storing an output. So similarly, I match this up to the output of cell 1, look up the hash from cell 1, deserialize it, execute in that environment with that deserialized value of x. And now I can tell that when I serialize x post-execution, the hash now no longer matches what it was previously. So I can interpret that x has been modified. So that then triggers x to be stored as an output for cell 3 in the cell node 3 map, mapping that to the hash of the new value. And that will be stored in the notebook data store as well. A side note here, I also keep track of the number of references to all of these objects so that I can clean them up as needed, kind of in a standard reference tracking garbage collection way. OK, finally, cell 4. Here, we're loading x again. Now the immediately previous cell in linear order that modified x is cell 3. So I'm going to look up the hash from that cell's map and deserialize the appropriate cell from the value from the data store and execute in that environment. And now x is not modified, so no outputs there. OK, so that's the way that execution works. Hopefully that was clear. So moving on then to the cascading invalidation. So as I mentioned, cells can track their validity. So a cell is considered valid if its inputs have been unchanged since the last execution, and particularly if its inputs are valid since the last execution. So if an input changes, then what the process that I will do is I'll mark any cell that depends on that as invalid. So suppose that I change cell 1 here, so that now x has another element. So I'm going to mark that, mark then anything that depended on what that cell previously outputted as invalid. So since cell 2 and cell 3 here both link up to cell 1, then I mark those as invalid. And then also this, I mentioned, is cascading. So I'll look up anything that depends on those cells' outputs in turn, which also catches cell 4. And then I know that if I want to rerun cell 4, that I have to rerun up the chain until I get to a valid output. OK, and then the last kind of property that I mentioned here is accessible intermediates. And I think this is kind of a handy thing for exploratory data analysis and inspecting kind of intermediate results. So if I want to add a new cell and I want to look at like what does something look like somewhere in this chain other than the end, I can insert that cell in this linear order. So suppose I have this new cell to calculate the max of x, and I put it in here between cell 2 and cell 3. Then we just stick it in there, shift the other cells down, and match up the inputs appropriately. So here we'll get the value of x from cell 1 as you would expect, kind of from the linear execution order. OK, so I'm going to do another quick demo here. This is kind of more in the data analysis kind of workflow. So this is also cribbing a scikit-learn example. This one, we're going to load the wine data set, which is a classification example for classifying different varieties of wine based on chemical properties. OK, so what I'm going to do here to trick you is I have this cell commented out, and it's going to be important later. So I build a train and test data set. I initialize a classifier here, which is going to just do PCA and then logistic regression. Kind of a silly example, but it makes for a decent visualization. So then we will fit that example. We'll do a prediction on it. And we can plot the PCA transformed values here. So you can see these different classes, 3 different classes here, and they're not super well separated. And if we look at the accuracy here, it's not that great. So we might be curious then, OK, what's going on? And if you look at the features data frame here, you can see that all of these values kind of have wildly different scales, which is going to mess up our PCA. So that's then when we can come back up to this thing that I skipped earlier. So if we uncomment that and run that to modify, so we've modified features here, right? And now things are on a standardized scale, subtracting out the mean and standard deviation. And now this has invalidated a whole bunch of cells, right? And that's what you can tell, again, paying attention to the X's there next to the cells. So now if I wanted to have this cell that was invalidated give me the up-to-date version, it can rerun the cells as needed, and our accuracy's improved a lot. I can do the same thing with this plot, and you can see that the data is a lot better separated here. Yeah, that kind of puts it into a slightly more realistic workflow. Actually, any questions about that before I go on, and anything about like yeah, what I've talked about so far? Mm-hmm. Yep. Mm-hmm. Sure, yeah, so if I wanted to, so let's maybe do something in here. So if I add something that has an output, so like, okay, if I want to look at X here, I can do that. If I want to like print X and then set another output Z, that's not going to invalidate anything because nothing depends on Z. If I set an output for Y, then that's going to invalidate anything that depended on Y. So here, since this cell used the value of Y, it's invalidated because this new cell set a new value of Y. So we can interpret that this will have to be rerun. And so if we execute down here, then we'll pull in that new value of Y. Yes?
It's still not really clear to me how you are determining when things change. Like,
Mm-hmm.
you basically just serialize literally everything in the environment and then check the hashes?
Yep. Yeah. That's exactly it. And I'll come to that again at the end. But yeah, I'll comment on the serialization briefly now, which is like, that's actually not as like, it's not as slow as you might think. Like, as long as you're working on kind of reasonably small data, like that serialization cost is not that high. There's other downsides of serialization, because there's some things are not serializable. There's third-party libraries like DIL and CloudPickle that can serialize a much broader set of Python than Pickle itself can. And that gets you like, so Pickle can't handle closures, but CloudPickle and DIL can handle closures fine. The only thing that I'm aware of that's like categorically not handled by any of these libraries is generators. So that's one limitation. If you want to define a generator, you kind of have to use it within a cell entirely, and not have it exist between cells. Anything else? All right. Okay, I'll go back to the slides. So, okay, so now I'm just going to kind of talk a little bit about some alternatives and future work. So, if you were around for the previous talk, the data flow kernel kind of has some very similar goals, which it implements persistent cell IDs with dependency tracking, and also has a lot of other features that I learned about in the previous talk as well. So if you didn't see that one, it was worth checking out the video. There's also this Reactive Kernel project, which they had a poster session the other day, and this is kind of based around implementing a kind of reactive programming paradigm in Jupyter, kind of with similar motivations to this as well. And the other things as well that I'm sure I'm not aware of. One difference of this implementation is, and partly because of kind of Notebook's status as a lighter weight kind of side project almost, is that it doesn't touch the IPython kernel. This has an advantage of it's the development and installation is kind of a lot less involved than if you need to implement a new kernel and a new front end as well. So it's implemented as basically as an IPython magic. So there's no extra kernel and just hooking into the existing functionality around magics. That has a disadvantage also in that it can interact poorly with other cell magics. And also kind of I'm doing things that are kind of breaking the decoupling between the kernel and the UI. And in the UI, I have to do some kind of ugly workarounds to make this work at all. I have to do some monkey patching on the code cell object, and it's not pretty, but it works. So that kind of leads into some limitations and future directions that I'm interested in exploring. So kind of three categories here: serialization, kernel, and UI. So I talked a little bit about serialization earlier, and it's no small thing. I'm serializing the whole cell pre and post environment, and that's expensive for large objects. It's kind of fine as long as for anything under a couple hundred megabytes, but once you work on any larger data than that, it gets a little bit laggy. And if you're working on 12 gigabyte data sets or whatever, you quickly either blow out your RAM or your disk space by going back and forth serializing everything. Kind of the one way to kind of handle that is to treat this as something for smaller scale sample exploration. Kind of, I like to think of it as an environment for doing quick iterative exploration on a small subsample of data. And then because I'm doing all of this tracking of cell dependencies, you can actually pretty easily extract all of the code that modified some input to create whatever output you're interested in. And so a pattern that I've kind of explored with that is shipping off that code to a remote execution framework that can handle running that on the full data set that I'm interested in. I didn't include that with Nodebook itself because it kind of depends on more on our specific internal tooling. So it's not necessarily like a general plugin, but you can get that kind of behavior as well. Okay, I got a little bit sidetracked there. So okay, so the other disadvantage of serialization, as I mentioned, some objects aren't serializable, most notably generators. So this kind of implicitly restricts you to the subset of serializable Python. Also, this one is fixable, I think, but the way that I'm doing reference tracking, as I described in the previous slides, is by variable name only. So the behavior is potentially unexpected if you have multiple variable names that reference the same object, and then you mutate one of them. I'm only going to be tracking one of those. So you could do deeper reference tracking to mitigate that, I think. But I haven't really explored that. It's kind of an edge case because at least when I'm doing exploratory data analysis, I've never really wanting to mutate objects with multiple variable handles anyway. So that hasn't been kind of a major issue. Another thing that I'm kind of interested in around making it so you don't have to necessarily do the serialization every time is to give the user more control over the serialization, which you could accomplish with having maybe a mix of different cell types. So I've thought about having the current behavior is every cell does this full serialization of its environment. And other things that you could also add, so I've thought of having also what I'm calling transient cells that basically the pattern that I imagine for these cells is that rather than serialize, they would just re-execute if their input is ever needed again. So you could imagine like a serialized cell that has all of its outputs cached, and then some transient cells that depend on that. And anytime you run one of those transient cells or one thing that depends on one of those transient cells, we can re-execute all of them, going back up to that serialized cell. And that would kind of let you play with the trade-off between serialization versus compute. So if you're doing something that might be like a memory-heavy operation, but computationally cheap, then you can imagine that being useful. And then also it might be useful to have to allow global cells as well. Maybe there's times when you want to touch the global state, but I think that should be something that you should have to be very explicit about, rather than the kind of way that that's the default behavior of standard notebooks currently. Okay, then the kernel. So as I mentioned, Notebook integrates with IPython as a cell magic. That's kind of an abuse of cell magics. So ideally, this would be implemented as a kernel instead. And ideally, we would kind of use the message processing framework to talk between a specific front end and the specific kernel that are both like notebook specific. That's kind of that's a lot more work than the kind of cheap and tacky way that I did this here. But I think that would be a good direction for making it a more stable project. And then also, I think there's a lot of interesting work that could be done on the UI end as well. Currently, the integration between Notebook and Jupyter is fairly limited. I haven't done much on the JavaScript end at all, kind of just the bare minimum of monkey patching to make this work at all. And most of the work has been on the Python kernel side. Future direction for this, so Jupyter Lab has nice advantages of much more extensive pluggability. Like it's built around having more reusable components and written in modern JavaScript. So that kind of gives a lot more leeway to play around with these ideas. And that would be a useful future direction for any more UI work on this. Some things that I would like to do in that direction. One is right now I'm not doing anything to respond to non-execution cell events. So I'm catching basically only things that happen on cell execution. But there's other things that you might want to respond to as well. So moving cells or deleting cells, I'll pick that up when another cell is executed. But it would be nice to be able to respond to those kind of on that user event itself. Another thing is the visibility of cell validity. So in the examples I showed, invalid cells were just marked by an X. It would be kind of nice to have maybe something where the output is grayed out so that it's more visually apparent to the user that that previously computed output is now invalid. Also, I think it'd be nice to, since we're maintaining all of this connection between cell inputs and outputs, we have these potentially useful to the user relationships of exactly what cells depend on. So I think that there could be some interesting UI work there around indicating what cells depend on what, which I kind of like mocked out a little bit in this picture here. And then also support for different types of execution cells. So on the previous slide, I mentioned wanting to give the user more control over exactly how the cell behavior works, and that would kind of necessitate having something besides just the one executable code cell, at least the way that I was thinking about it. And I think that's it. This is on GitHub. I'm happy to have other people take a look at this, work on it as well, if anybody's interested in kind of taking this further. And also, I think we have plenty of time for questions too.
Where do you think yours lies in terms of easy to pick up, usability? Like, I mean, obviously there's sort of complete UI stuff you know it's fixed, but in terms of usability patterns of the systems.
Yeah, right. So I think that like one of the I think one thing that makes it fairly different from other things that I've seen is the way that I'm handling dependency tracking via serialization. So I think that comes with pros and cons. It's I think it leads to kind of more intuitive behavior, at least for me, because you can get a lot out of that in terms of like making sure that the environment that the cell executes in is exactly what you want it to execute in. So if you're not doing that, it's kind of really tricky to get around the problem that at the heart of it, everything is mutating global state in some way. Like Python is not really good about having immutable objects in general. So so to make this work the way that I wanted, I kind of had to hack immutability into it, right? And the serialization. The serialization gets you that in like a very thorough and kind of foolproof way, but also comes with some cost and some kind of edge cases that introduces as well. For me, I find that this kind of encourages me to write notebooks in the way that I want them to exist, with like a lower barrier, because it removes the need to think about like this cleaning up step. Because I am maintaining linear execution, so that's a property of it that I really like for my own work, is just everything is linearly ordered, and if you accidentally do something out of linear order, it's immediately not going to work, and you're going to immediately see why. So rather than having something where like you can very easily not realize that you did something out of linear order. That kind of keeps you honest and removes that kind of mental load for having to reason about whether or not something would be linearly ordered, or what you'd have to do to clean something up to be linearly ordered. So I don't know if that answers your question, but that's kind of the aspects of it that I like.
Do you serialize the hash or do you serialize the store?
Yeah. So let me go back to the serialization. So right. So what I'm doing here is I'm serializing the object, and I'm computing the hash of it. So the hash is what I'm storing alongside that cell, but the full serialized object I'm storing in a global store and linking to it via that hash.
So could you store it in memory?
Yeah.
Serialize?
Oh, I can serialize to memory or a disk. So I'm serializing it. Oh, like, are you asking whether I need to serialize at all?
You need the deserialization.
Yes.
You just keep it in memory.
Sorry. So is the question around whether I need to serialize or not, or whether it's a serialized to memory or not?
You need to serialize the hash to figure out if it's true.
Yeah, I also need to serialize to get immutability. So if I'm not serializing things, like if I'm just like sticking it somewhere else, then something else can mutate that object because like references to it still exist. But by serializing it, I guarantee that there's no references to it anywhere. Nothing can mutate it. It's frozen. Anything else? Cool. I'm not sure if are we at time? No. Okay. But I guess we'll end a little bit early then.